That's all. Right now? This one is
All right. We just learned chain rule last week. So we, on the board, we have a practice question for chain rule. We have a function that's defined by square root of 3 minus 2x. And I don't know if you remember the derivative of square root of x is 1 over 2 times square root of x. So we do that as a derivative of the outer function. Like if the original function is square root of x, then the derivative is 1 over 2 times root of x. A pair of relation between the original function and the derivative function. Now, this is not square root of x, it's square root of 3 minus 2x. So there's some extra thing that we'll have to calculate. So all these, they're kind of similar, but try to figure out which one makes sense. Let's see all the inside you entered. Let's see. It's not a, you have to apply chain rule, you have to find the derivative of the inside function. So let me try to write it out. We've got to remember that we have to apply chain. That is, we will find the derivative of the outside function and you want to find the derivative of the inside function. So on the outside is a root function. So if you take the derivative of the outside function, it will be 1 over y prime 1 over 2 times square root of 3 minus 2x. This is because the square root is the outer function. But also after you've done that, according to chain rule, since it's not root of x, it's a root of 3 minus x, you still have to find the derivative of the inside. So you have to multiply the derivative. You see the derivative of 3 minus 2x is, what is it equal to 2 minus 2x? Negative 2, right? So this has a derivative of negative 2. And then we also will multiply what was originally there. Right, so the grain is the correct answer. Make sure that you double check. If you think the answer is A, and then you probably didn't calculate or you didn't factor in the, that's still not right. No, you didn't factor in the inside. See, we multiply this with negative 2. This, if you multiply it, is negative 2 times 1. So it's negative 2, and this is a 2. This is root of 3 minus 2x. So in everything combined, this is the same with multiple choice. I have to simplify until it's similar to some of the answers. You will combine and then have a 2 in here, you have 2 in there. If we cancel the 2, we would actually have a negative 1 here and root of 3 minus 2x. So after everything is simplified, that is the final answer. So, sure, that's not the one. Okay. It's right. Let me see if everybody can see. Yeah, I got all 11 correct. That's that's everybody. That's everybody. All right. So didn't see your card. Yes, so the answer is B. So it's kind of surprising. So just try. So sometimes we forget to do the chain rule. Because if you only differentiate the roots, you'll see something similar to this. But then that's not all. That only is when you consider the root part of it. And then the inside have to have an impact, have to have that extra number that we multiply. The example from section 5. Do you have any homework questions?
Number 8.
Please. Right, so this is one of the situations we separate the notation. So when you have the notation separated, this is really look at the construction of the function. So let's look at the first question. Is you put in the inside function into the outside function. That is, when you plug in this function to the function f, you're replacing the u by g of x. The expression of it will be this is f of the f function is whatever input is, you take tangent of it. Okay. Now we're putting the g of x in there, and what's the g of x? The g of x is actually x cubed. So you're going to plug in x cubed in here, and also here. So the first question is the construction of the composition function. That's the first one. Will answer tangent of x cubed. Second question. So you have to look at the function one by one separately. Second function is when you look at the derivative of the function of the f function by itself. That is, we do not plug in the u. We're just looking at the derivative f from the u. Derivative of f function is the derivative tangent. Derivative tangent is secant squared. So that's just the secant square of u. So we're just looking at the derivative function without looking at g at all. So just f by itself. That is the derivative of the outer function. Now consider the second function. All right, and then the function below it is look at if you have the derivative of the outside function, we're replacing the inside function in the outside function. That is consider differentiating the outside function without changing the inside function. So so we'll have to keep track of the notation here, which says at prime of the input, you would take secant square of that input. Okay. Now that's the derivative of the outside function. But then according to question 3, we're putting the g of x as a u. So we would put in x cubed in here. Therefore, there's x cubed. Okay. So if you want to find f prime of g of x, you're doing this. Okay, so the answer for that one will be secant square of x cubed. So this function is really doing the chain rule little by little to see all the pattern that you can observe. First, you differentiate the outside function, which is what we're doing. And second, you differentiate the inside function. When you're differentiating the inside function, this is the inside function. So we're differentiating a power of 3. According to power rule, this is 3x squared. Right. This is the derivative of g of x by itself, so there's no other consideration. And then lastly, is combining everything. Remember, chain rule is multiplying the outside function, which is this one, and then time the derivative of the inside function. So we're actually combining these two, multiplying them together. That's the chain rule. So the answer to the last question would be the actual derivatives of secant square of x cubed. The outside function times the derivative of the inside function. So the last function, the last question, answer to the last question is combine everything before it. So let's see how we enter all of them. The second one is secant square u, with u being the actual variable. The third one, there's no u. We're plugging g of x, so secant square of, now u is being replaced by x cubed. And this one, we actually going to differentiate the inside function, that's 3x squared. And then last one is we multiply everything. So this one is being multiplied by. So this is multiplying inside function. That's my number 8. I wonder what was the difficulty that you had?
It was just on the last part.
The last part, okay. Any other questions for section 5?
Number 9 as well.
Number 9, okay. All right, so this is you're given a function and you have the task of identifying the inside function and the outside function. So and this you're gonna have to develop your own idea of what's the overall structure or what's the detailed little function that was stuck in there. So if you look at it, this is overall is a power of 4. To me, like it's something to the power 4. So the power 4 to me that is the outer function that is taking the input and making it to a power 4. And then other than the power 4 part, everything that is stuck inside is considered the inner function, the inside function. So I will write x plus sign of x as the inside function. Right? Once you identify the inside function, outside function, you will apply chain rule. That is, you find the derivative of the outside function multiplied by the derivative of the inside function. So here we're gonna put x to the power 4. So the f is whatever was outside, and this is the x plus sign of x. Now, last one is the chain rule. You differentiate the outside function. That is the power of 4, and don't do the x part because we don't have x in the power. We have this for the power. So whatever is taken to the power 4, you have to move the 4 to the front and lower the power by 1. But in the meantime, we're keeping the inside. even though we're calling that being the outside function, that is f of this big thing is equal to this big thing to the power 4. So that x is really a holder for any input, the actual input. So when you are calculating the derivative, you will move the 4 to the front, and then x plus sine of x is raised to the power 3, and that's differentiating the outside function. And then we're going to multiply differentiation of the inside function, which is 1 plus cosine of x, and I finished the entire application. So if there's anything new that is f of x that's different than what we have there, but we're just trying to figure out the overall structure. That's why I'm trying to write it over here. You want to see what was the whole, what was the overall, the first thing or the last calculation. I hope that kind of explains.
You should answer
Oh, which one?
the other one, the answers.
The answers. I already have answers to the first one and second one. The last one. That's the differentiation of the outside function is power 4, so you move 4 to the front. Power minus 1 is power rule. N times whatever is taken to the power minus 1 is power rule. And then we multiply the derivative of the inside function. Derivative of x equals 1. Derivative of sine is cosine. We multiply this within the parentheses. Turn into a whole derivative. Make sure we add parentheses for everything, especially this pair. Sometimes I have students forget to do that. That would be wrong. You see, it's kind of important to know that it's a derivative value. 1 plus cosine is being multiplied. If you don't have the parentheses, then the computer will be like, well, what is that? So without the parentheses, actually incorrect. So make sure parentheses to check the order of operation. So you have to have 1 plus cosine first, and then multiply to the derivative of the outside function. Any question? Any other questions? Number 10. All right, so this again is chain rule. We'll do it. Try to do it one by one. There's it's just like peeling the onion. There's outside of the outside, there's an outside. So you have to kind of do it step by step. All right, so if we're differentiating this, realize the most outside function is the cosine. So because of cosine, when you're differentiating, you want to find the derivative of cosine, which is negative sine. So we have negative sine. And that is the derivative of cosine. But as you are differentiating the outside function, we do not change anything inside of it. So we'll keep all the inside. Sine of x squared. So it's like you peel the onion. You peel the outside only and don't change the inside. You will do it when you get to it. So we finish with the cosine there. Once you're done with that cosine, the inside, this side, we're differentiating sine of x squared. So it's like calculate the derivative of sine of x squared now. All right. So once you finish with the outside layer, you can forget about it and only deal with sine of x squared. The derivative of sine is cosine, so we have cosine. But whatever was the input has to be there. There's no change to the x squared. It's not sine of 2x, it's cosine x squared. So keep the x squared, only differentiating the sine. And then lastly, now we finish with that sine. So you're done. And you move into the layer, the inside layer. So take it, you peel the outside or deal with the derivative of the outside function. Once you're done, you're looking at only at the inside. So after the cosine is gone, the sine is gone, we have x squared. The derivative of x squared is 2x. Right, so this is applying chain rule 2 times as we go. Any questions? So that's the derivative. Most of the time we actually tend to move the x or 2x to the front, just so it's easier to write. So negative 2x, and then we have cosine of x squared, and then we have sine of sine. That would be again with multiplication. You can always rearrange them. I have a 2x over here, but actually move it to the front, just so it looks a little bit easier. It's question 10. Any question? Number 4?
Yeah.
You want to look at your number 4?
Yeah.
All right, we can look at it together. All right. First is the point, and you can see that it has a lot of decimals. We're looking at the y value with x equal to 3. So this is 3. 2 plus 2 times 3. That is 8. So the y value is actually 3.8 over root of 8. So that's the point. And to find the tangent line, we also need the slope. The slope would be the derivative. It's the derivative at 3. That's the one we are calling at m. All right, so we gotta know the number. The slope determining the direction of the line. The point determining the location of the line. We need both information for the tangent line. So let's find the derivative. Y prime. So y prime has a notation. To make it easy to find the derivative, we can write into a power form. This is 3.8 multiplied by 2 plus 2x to the power of negative 1/2. It's a root, that's why we have 1/2 power. It's in the denominator, that's why we have negative. All right, so when we try to find the derivative, we'll multiply the negative 1/2 with 3.8. To get negative 1.9, and the power has to minus 1. So it's going to be 2 plus 2x to the power of negative 1/2 minus 1. It's negative 3/2. Right? Negative 1/2 minus 1 is negative 3/2. That is the differentiating, that's the power rule. So according to power, we multiply this with this, it's that one. And then power minus 1. All right, that's just because of this and this, which we got that one and that one. And we didn't change anything in the middle. And then you have to multiply by 2, because according to chain rule, we should find the derivative of the inside times 2. Because derivative of 2x equals 2. And that finished the whole differentiation. Okay, so after we've done, you realize that there's a negative 1.9, there's a 2, we move it out to the front, it's negative 3.8 times 2 plus 2x to the power of negative 3.5. Okay, that is the derivative, but that's not the slope. The slope is the derivative value at 3. Y prime at 3. We're going to plug in a 3, so it's negative 3.8 to the power of, this is 3. So 2 plus 2 times 3, which is 8. So it's like 8 to the power of negative. Negative 3/2 is negative 1.5. That's the slope. So now we can write our equation of the line. So equation one is like y equal to m, which is, that's our n, times x minus x0 plus the y0. So here is our x0, and this is our y0. So the equation will be equal to negative, that was a slope, negative 3.8 times 8 to power negative 1.5. And then x minus x0 is minus 3, and that was plus 3.8 over root 8. So that's our tangent equation. Are we okay?
Yeah.
Yes?
How did the 3.8 become
Because it was negative here. And that one time, this one is negative. So that was a tangent line equation, because the question asked for the y-intercept, meaning that we are making the x equal to 0. So if this is your tangent line equation, but you only want the y-intercept, so you're going to make that one with 0, and that will be y-intercept. So if you already have the tangent line equation, which has the x, which has the y, but if you only want the y-intercept, make the x equal to 0, then that would be the y-intercept. So you have the tangent line equation, finding the y-intercept is basically replacing the x by 0, or you just choose not to write the x. Because 0 is normally 0 minus 3, you just write minus 3. 0. And that's the y-intercept.
How did the negative 1/2 turn into the negative 3/2?
It's minus 1, and whenever we apply power rule, according to the power rule, if you have x to the power n, then the derivative is n, and x to the power of n minus 1. So we're moving, this is a n, move it to the front, that's why it becomes negative. And then negative 1 point, negative 1 over 2 is the n, which minus 1 is negative 3. Any other questions? Number 4 is kind of complicated because the number itself is square. And then you can see the number is all calculation, no pattern. It worked?
Yeah.
Okay. Any other homework questions? I hope that we're able to complete all the 2.5 homework. So far in class, I think we did every single question on 2.5. Oh, that's yours.
Yeah.
So mine, I obviously have the staples here. Anyway, so today we're gonna move on to section 6. All right. So 2.6 is the one that's harder than the other section, I think, because it's the one that normally did not have a formula. Like product rule and quotient rule, we got a formula. If you follow the formula, you have some pattern. And then in 2.5 we have chain rule. At least you can grab the outside function. The 2.6 is called implicit differentiation. The word implicit is the opposite of explicit. Most of the function that we deal with is explicit. Explicit function is when you have y by itself, you have a formula y equal to a formula of the y. So, for example, y equals 3x squared minus 7. That is a explicitly defined function. So if you want to find the derivative, you find the derivative of this variable part, and that gives you 6x. But sometimes you have a equation which represents the relation between variable x and variable y, and then from that equation you can solve it like example here, right? We don't see the y by itself, so you can work out the algebra and try to get y by itself. You can move this one over and then have the negative, or you can move this one over, move the pi over, and y equals x squared minus 4, and then you find the derivative. So sometimes we can convert a implicit defined function into a explicit function. So if the function y is not by itself, you can make it by itself, right? That's how you can solve the derivative. But sometimes the function is so complicated that it is almost impossible to have the y by itself. For example, this one. And we have sine of y plus y cubed equals 6 minus x cubed. So obviously on the left, you have relation formula of y. On the right, you have formula of x. And we have no way of solving the y value. You can solve the x value instead. So what if we want to find the derivative? So why do we want to find function like that? Sometimes you also want to find such as slope of the tangent line. You want to find the change at the particular location. So it feels necessary to find the derivative even if we have no formula for y. This is actually an interesting function. So let me try to graph it for you so you can see why why we want to find derivative of that kind of function. What's our minus? Plus. Okay, this is how it looks like. Right. And you can see overall it kind of follows when the x and y are really large. Remember sine is actually a really small value. Sine value is between negative and positive 1. So when y gets really large, sine is still very small, like smaller than 1. So overall you have y cubed equals 6 minus x cubed. So in the overall tendency, when x goes to infinity and y goes to infinity, is y equal to negative x. So the main relation between x and y. But locally, around 0, right? When x and y are both small, this sign is affecting how the graph behaves, right? So then it even have some kind of symmetry. So it kind of makes sense to have something. Sometimes we have like parts of the machine behave like shape like that. So very smooth curve, and that's this kind of thing that it can seem odd and unrelated to real life, but then actually have everything to do useful for certain purpose. So anyway, because for this kind of function, we would want to know the derivative, and we will be like, how to find the derivative without actually having a formula for y. And this process is called implicit differentiation. Right, it's finding the derivative without knowing the formula for y itself. Oh, it already have the graph. See if I want to find, I want to draw a tangent line there. If I want to find tangent line over here, I would want to find the derivative. All right, so what do we do? The process of the implicit differentiation is based on the chain rule. So if you got a very complicated function, you try to find the derivative. This is the chain rule. You would differentiate the outside function, keep the inside, and then multiply the derivative of the inside function. Now, suppose the function g of x is not given. Say I don't have a formula for the y, so I write f of y. But suppose I consider y as a function, so y would have a derivative. Therefore, y is not an individual variable, it's a dependent variable. When you try to find the derivative, you would have f prime of y being y inside function, and I have to multiply by the derivative of y. So it has something extra. You see, if y is a variable I solve, we would stop here. But if y is not a variable, y is a function, then y would be the function that's stuck inside another function. So that is a convolutional function. Right, like y. So when you interpret the variable affected how do you differentiate function? Right, so that's normally how I would write it. This is shorter, but in some book we would write dy dx instead of y prime. This is what we're going to do. You're going to see a little bit extra whenever the y is being involved. So we want to watch out whenever we're differentiating any term by variable. So we're going to start with that function in the graph we already have. Let's try to do implicit differentiation. And the process is kind of similar to how we deal with many of the mathematical equations. If you have an equation and if you do anything to one side of the equation, you do the same to the other side of the equation. So for example, let's say I want to find the derivative, meaning that I want to find the derivative on the left, being y as part of the function, and then I will differentiate the left side of the equation as well. So we will find the derivative of the left and differentiate the derivative of the right. I normally call this process differentiating both sides of the equation. So say differentiate, it's a verb, differentiate both sides of the equation. The equation provide a relation between x and y, and therefore it is an implicit defined relation between x and y. So we would differentiate left side and right side of the equation. Obviously, the right side is easier because the x is the independent variable. Derivative of 6 is 0. Derivative of negative x cubed is negative 3x to the power. But that's what's on the right side. But we will have some issue differentiating the left side. We start with the sine y, and remember chain rule. So we have to keep telling us that every time you differentiate anything involving y, you will be careful that you have to apply chain rule. For example, if you're differentiating sine y, derivative sine is cosine. And again, whenever you differentiate the outside, we never change the inside. The inside is still y. And that's done. That's done for the outside function, the derivative of sine. But then remember, y is not a variable. Y is a function. So the y is a function inside the cosine. So that's a composition function according to chain rule. We have to multiply the derivative of y, which we call y prime. Right? And then you can see the differences between what's in the past. If you got sine of x, derivative sine of x is cosine x. But if you have sine of y, derivative of sine y is cosine y times y prime. All because we assume the y is a function. If you see y as function, then you have to multiply the derivative. And because that extra thing, we're able to solve it. Because only when your function has y prime, you'll be able to figure out a formula for it. If your entire problem does not have y prime anywhere, then we have no way of solving it, right? It has to show up somewhere for you to find it. All right, and then we do the same. We are trying to find the derivative of y cube. That's a cube function according to power rule. We move this 3 to the front, and then the power has to become power of 2. But that's not all of it, because this is a y function. That 3y squared is differentiating the outside, which is power 3. And then you have to multiply the y prime with it. Then finish the differentiation of y cubed. Any questions so far? This is the implicit differentiation. The process of assuming y in a function, a hidden function, implicit function. It causes us, every time you see a y showing up and you're differentiating, you have to multiply by y prime, because y is a function. So now we end up having y prime in a whole setting. And what we're going to do is really find a formula for the y prime. These two terms has y prime will have cosine of y plus 3y squared. Because there is a y prime, I consider y prime a common factor, so I factor it outside. And this is equal to negative 3x squared. All right, and then I need to find a formula for y prime because I want to know the derivative. So y prime is now equal to negative 3x squared divided by, so this extra thing that we multiply the y prime become a coefficient we divided, so then the y prime can be by itself. Right, so that's the answer to the differentiation. The question says find y prime, and now we have a y prime formula. So even though we do not have a formula for y, but now we have a formula for y prime, the derivative formula.
Wait, where did the second y prime come from? The one being multiplied by 3y squared?
This one, your derivative y cubed is 3y squared, but y is a function, so y is the inside function. According to chain rule, we have to multiply the derivative of y. It's the same that y cosine y has y prime. Because you differentiate the sine, you get cosine y. But then the inside y is a function, so you multiply the derivative. That's also the differentiation. So whenever you have a function inside of it, it's multiply the y. Any question? This is multiplied. So what our interpretation affected how we deal with it. If we think that they are variables, then we don't have to find the derivative. If we think they are functions, then we have to find the derivative every time we differentiate it outside. So this gives us a formula for the differentiation. Right. With that being in mind, now we want to find the tangent line equation. And that was a special point, root of 6 and 0. Is a special point on the graph. So say that was a cube root, right? Cube root is 1/3 power. So 6 to the power 1/3. That's 6 cube roots. And then 0. That's that point. Right? You can see it has a negative slope, and here we're going to try to determine a tangent line for it. For this point. Okay, we got a point, and then we have to know the slope in order to write the tangent line. Okay, so since I already have the formula for the derivative, I'm going to keep that part and just put it in there. All right. So if you're working on finding the tangent line here, you're going to still have to do all that, and then I'm putting all that already here. So now we already have the derivative function. So as usual, when you're trying to determine the equation of a line, you need a point to control the location. You need the slope to control the direction. We already have the point. The point is this number, and then all we have to do is figure out the slope. So this is our calculation. I guess it should use a different color. Negative 3x squared, and then the x is this number. So we'll use negative 3 times. This is cube root of 6, okay, which equals 6 to the 1/3 power. So to make it easy, I'll write 6 to the 1/3 power. And then we have to square this. That was the x, and then we square. Just want to make it easier to enter. This is over cosine of y, and y equal to 0, so this is cosine 0. If you look at your calculator, cosine 0 equal to 1, so that is actually 1, plus 3 times y, and then y equal to 0. And that means 0 squared, that's basically 0. So the denominator equal to 1 plus 0, cosine equal to 0, and then which basically equal to 1. All right, so this is 3 times 6. When you have power inside the power, you multiply the power. So 1/3 times 2 is 2/3 power. And then again, the division by 1, you can write it. So slope basically is 3 times 6 to the power of 2/3. That's our m. It's the m.
Wouldn't it be -3?
Oh yeah, -3. I lost the negative sign. That's negative. Thank you. It's a negative slope. So now we can write our equation. The equation would be y equal to the m, which is -3, 6 to the 2/3 power, and then multiply by x minus the x value. This is the x value. So x minus 6 to the 1/3. I'm supposed to write cube root, but it's harder to write cube root if you were trying to enter out decimals. And then we plus the y value is 0, which if you don't 0, you don't 0. So that's the tangent line equation. And we can confirm that by graphing it right there. Y equal to -3 times 6 to the 2/3 power. And this is multiplied by x minus 6, 1/3 power. That's the x. And you can see it's tangent to. Any questions so far? So this is the equation of the, like this equation to the tangent is. So let's move on to another example. We're probably gonna do a lot more. This is really depend on your function, right? What's implicit differentiation? So in implicit differentiation, you assume the y is a function of x. Or assume y, whenever you see a y, you kind of remind yourself, hey, this is the function. And whenever I see it, I gotta make sure I have the y prime. So we're gonna take derivative of each term in the equation. Derivative of the left, take derivative of the right. Whenever you see an x term, you would do the same as what we have been doing. Just take derivative of the function. And then we are taking derivative of the y term, right? We still use the same rule. We have product rule, quotient rule, power rule, chain rule, but make sure you always multiply y prime whenever you are differentiating a term as y prime. And then that causes a lot of y prime in your equation, because every time you see a y term, you multiply y prime. So sometimes you see a term that has y prime, sometimes you might see a term that has no y prime. So you're going to collect all the y prime terms on one side of the equation, and then solve the y prime. Solve the y prime by dividing. Normally, the last step of the implicit differentiation is a division. So if you're using implicit differentiation to find y prime, normally your prime ends up being a division. Any question? So we'll be doing the same process. All right. Let's try it one more time. So you're able to get similar answer. What's on the board? So we're gonna find again. We're gonna try to find the derivative. This is also another example where finding the y prime. Finding the y by itself is kind of hard. This is degree 4, and this is degree 3, so it's kind of hard to find the derivative. Another issue is that by now we have many rules, and if the function has a simpler format, then we might apply one rule, and that will be it. But if the function has a complicit format, we might end up having to apply multiple rules, so we gotta make sure we keep track of it. So for example, we will first differentiate both sides of the equation. Just write that down. So let's find the derivative of the left side and the right side. Both sides. Right, if you're trying to find the derivative of y cubed, you will be getting 3y squared, and then you have to multiply the y prime, because y is a function, right? And then plus, it will not be as simple when you are doing this, because this has a function of x, this is a function of y. Y is also a function of x, right? So that's multiplication, so we have to apply product rule, right? We're gonna have to apply product rule. So in that case, we want to be careful what we're exactly differentiating. So I'm gonna follow strictly the product rule, which is we differentiate the x squared and keep the y to the fourth, plus we're gonna keep the x squared and differentiate the y to the fourth. So I'm trying to use notation to make sure I'm doing the product rule correctly. Because sometimes when we're rushed, we tend to make small errors, make small mistakes. So we're gonna find the derivative of the right side, derivative 1 equal to 0, derivative 2x equal to 2. So that's 2 on the right side. So far we did some calculation, but we didn't finish all of them. So let's continue. And then this part will keep the 3y squared times y prime plus, now this step we have to find the derivative of x squared. Derivative of x squared is 2x. See, in this step we're not differentiating y to the fourth, so we don't have the extra y prime. when we're doing this one. So that you will get 2x because that's the derivative of x squared. And then the y force is part of the factor. There's no differentiation for the y term. Right, now this one, we have the x squared stay. We're differentiating this.
How do you get the y squared?
This one,
No, down. Wait, instead of y prime, you put y squared.
that's, yes, it should be y prime. I was wrong. It's my mistake. Yeah, sometimes I don't know what's going on. It should be y prime. That's definitely a mistake. Yeah, 3y squared times y prime. Thank you. Thank you. All right. So up to this stage, we should multiply the derivative y to the fourth. That's the power 4. So according to power rule, we have 4 and y to the power 3. This is a process differentiating y term, so we multiply by y prime. Extra y prime there. This is equal to 2. All right, and then you can see that sometimes we have a y prime, sometimes we don't. It depends on whether you are actually differentiating a y term. So over here, we're actually differentiating the x term. The y term is just coefficient. We're not really doing any differentiation there. Here we're differentiating the y cubed, but that's why we call the y prime there. And this is why we're differentiating the y to the fourth, which is why we have the actual y prime. And you have to be careful when you need a y prime, when you don't. Here, there's no y prime. So we end up having two terms that has a y prime, and then there's a term there that doesn't have a y prime. Normally, we'll move the one that has no y prime to the other side of the equation. So we'll subtract the 2xy to the fourth, just so all the y prime term is on one side. All the one that has no y prime will be on the other side. So minus 2x to the fourth. Right, and then when that one gets moved, there's two terms left. 3y squared y prime is one term, and plus, I like to move the fourth, the one to the front, so 4, then x squared, y cubed, and then y prime. So there's two terms on the left and two terms on the right. So 2 minus 2x y to the fourth. And then we would factor the y prime. You want to make sure there's only one y prime. So we get y prime all side. And then this is 3y squared plus 4x squared y cubed. And then y prime is on the outside. This is equal to 2 minus 2x to the fourth. And lastly, we want to get y prime by itself. So y prime is equal to a big division, whatever on the left side, divide by all the factors that we had on the right side divided by left side, divided by 3y squared plus 4x y cubed. Okay. Any questions so far? Right, sometimes it does get complicated. You can see there are two terms in here, two terms there. We might sometimes lose track of the process. So if you wish to have like double check your work, there's I think I mentioned it before. You can try single lab. Single lab. Right. That way for this, you will just enter implicit. Derivative, and you put your equation in there. This was equation. Right, so right, what was the first one? It was y
Cubed.
I cubed plus x squared.
Yeah.
A to the fourth power.
Yeah.
It equal 1 plus 2x. L does that. And then you can see the result. And down here, you see some of the process. It's not very complete though. Sometimes you might have to. I think they try. They also kind of try. They think that they try to lure more people to get membership and stuff. But most of the time I'm okay with that one. And just double check our work. For example, we have this answer already here. See the division. Simple like it factor the y squared. There's a y here. There's a y. You factor the y squared out to have a multiplication. But it's basically the same answer. The numerator also have a common factor too, if you want to have. But for the most part, I think we have the same answer. 2 minus 2x y to the fourth divided by 3. If you multiply the y squared, it's 3y squared plus 4x cubed plus y cubed. Basically the same answer as we have. Any question? All right, just want to provide one more source where you can confirm all of your calculations so you don't feel like totally lost. With practice, we can get better. I feel like implicit differentiation is definitely something that's slightly harder than the other assignment. Right, so one more time. Again, this is when you have complication in mainly the sign part of it. All right, so let's do 3 more examples. The process. Okay, so again, we're trying to find the derivative. Basically, you want to try to come up with a formula for y prime for the derivative. And we just want to know the derivative, even though the function is not be explicitly defined. So we will try to differentiate the left side and the right side. When you try to differentiate the right side, somehow the right side tends to be easier. Derivative of the x equal to 1. Derivative of the y is y prime, right? That was the original. This is the derivative. That's all there is. So there's nothing complicated on the right side of the equation. You can also think of it this way: derivative of x equal to 1, or derivative of y equal to 1, but then y is a function. Like, this is really 1 times 1. That's just 1. That's 1 times 1 time. Because y is a function, x is not. X is an independent variable. So there's a difference between the variable and the function. All right, now we're going to look at the left side. It's more straightforward for the y cubed because it's basically the power function of the y function. So you apply the power rule, you have 3y squared. Move the power and then power minus 1. But this is the y term, so you have to multiply by time. We're differentiating the y term. So for this part, we're okay. And then there's a complicated part. So when you try to differentiate the sine of x squared times y squared, derivative of the sine is cosine, right? Right? So whenever we differentiate the outside function, we don't change the inside. So we end up getting a cosine of x squared y squared. So when we write down the cosine part, we don't change the angle. We do not change the inside. But then they're the same. We have to do differentiation of the inside. The inside is a complicit. It's x squared times y squared. And I'm writing a notation there saying I did the differentiation on the outside. That's why I get the big cosine part. Now it's time to differentiate the inside. So instead of doing it one step, I'm writing the prime notation there indicating this is something we're about to do instead of having all in the same step. So I'm trying to make it several steps so we can keep track of the process. I hope it's okay. Right? At least that part was correct. And then that way you at least will get some partial credit for writing this part down. And then we're going to move forward. This is a multiplication, so that part you actually have to do product rule. That's why it's better to keep track of the steps. And then the next step, you still have the cosine part, and that is going to be part factor all the time. Now we're differentiating this part, then what we're going to do is we do product rule. So according to product rule, we have to find the derivative of x squared and keep the y squared, plus we have to keep the x squared and differentiate the y squared. All right, so I'm trying to write out the product rule little by little, so we will at least have the structure correct. That's the product rule. And again, this is not the final step because I'm still doing a little quantification on the outside parentheses to indicate, hey, this part got to be differentiated further. This part needs to be work on more. At least all the other part are done, so plus 3y squared, and then y prime, this is equal to 1 plus y prime. All right, let's finish this part. So we have cosine of x squared, y squared, multiplied by, now x squared differentiated is 2x, and then we multiply by y squared. See, there's no y prime, because right here we're differentiating x term. It's an x squared that we're finding the derivative for. But now this step, x squared is coefficient, differentiate y squared, you have 2y. But with that, this is differentiating a y term. We have a y prime. Y prime. So plus 3y squared y prime, which equals 1 plus y prime. By now we have differentiated every single term, but there is still something that we have to work on more because we have this extra parenthesis that's distributed. So you have the big cosine multiplied by 2x y squared. So we will write 2x y squared times cosine x squared y squared. Cosine is a big number, so it looks like a big thing, but there's no multiplication. It's not cosine times x squared y squared. It's cosine of this whole thing, and therefore we can't simplify or break it down or combine. So you just have to copy it over. So plus this cosine is multiplied by this part, and I'll write 2x squared y cosine x squared y squared, and then it's the y prime plus the 3y squared y prime, which is 1 plus y prime. Okay, so there's no more actual parentheses, except the one with cosine that we can change. All right, last thing is we have a habit of writing y squared, obviously. There's y prime. And we have to get y prime by itself. So there's a y prime here, a y prime here, a y prime there. So there's actually 3 terms that has y prime. So we'll have to move everything that has no y prime to one side, everything that has y prime to the other side. So after we move everything, it'll be this. So this one, the 2x squared y cosine x squared y squared, there's y prime, and plus 3y squared y prime, and then minus the y prime. I'm moving that one over. Okay, so this is everything that has y prime, and then everything that does not have y prime, let's move it to the other side. So it's 1 minus, it was on the left, so you move it to the right. That's why it has a minus, minus 2xy, that one, and move it to the right. So we have cosine of x squared y squared. So we're almost done. All we have to do is factor out the y prime, that y prime, this y prime, this y prime. The rest are multiplication, so you can't separate them. They become one big thing for the y prime. So kind of need a little bit more space.
In the green, where do you see the second term from?
This one,
Yeah.
that cosine, I multiplied this one to get that. This cosine, there's a parenthesis that cosine multiplies this big thing. So multiply the cosine with the each term inside of this. This one multiply the cosine, it's this. This is just distribute. Yeah, I distribute the cosine with the big part.
And then so we can end up taking just the y prime stuff.
Right, yeah, this one has a y prime, that one has not, and you kind of have to remove that parenthesis in order to,
Separate.
yes, in order to separate.
Oh, so you just move the 2 to in front of the x instead of in front of the prime.
Yes,
Okay.
yeah. I moved that to, because it's a tradition to, most people have it to have the number before the variable. So if I have a number in between the in between the variables, I'll move it to the, that's why, yeah. All right, so finally, once you get y prime by itself, it's gonna look like, so So look like this, y prime is equal to 1 minus 2xy squared cosine x squared y squared. That was all the term on the right. On the left, we have 2 cosine squared 2x squared y cosine x squared y squared, and there's plus 3y squared, and there's a minus 1. I'm looking at this. If you get the y prime by itself, that's the whole term. That's the last step, which is the division. The right side divided by the left side coefficients. Because the y prime is now a common factor. Other than the y prime, all the other terms are divided.
So that minus y prime becomes just a minus one.
Because I have the y prime factor outside. I guess I skipped one step. So if you get y prime by itself, then you see all the other stuff like the minus 1 and
Yeah.
the 3y squared and the 2x squared y cosine. And that's why we divide it.
Yeah.
Any questions? So this is the one that's slightly more complicated because we have chain rule. And we also have a function that's multiplied. When functions are multiplied, you have to apply the product. Some part involve differentiating x terms and differentiating y terms. So we gotta be more careful. I'm also one that tend to, whenever the multiple steps, I tend to copy the wrong things, and we gotta be careful with that. I'll have it with things. And this that it will. Couple other examples. Let's see if we got time. All right, this is a question related to, this is related to a circle. X squared plus y squared equal to 1 is the implicit defined function, which has a, right, so if you have x squared plus y squared equal to 1, it's a circle. And this is a circle that we call the unit circle, right? Sine squared plus cosine squared equal to 1. This circle is not, the function is implicitly defined. If we want to define the function, you have to solve for the y. So you will move the x squared, so y squared equal to 1 minus x squared. You're going to take square roots, and you have y equal to square roots. Root of 1 minus x squared, right? Yeah. So that's how it looks like, right? It's only the upper half. So if you solve for that y value, it doesn't really replace the original equation. So the equation x squared plus y squared still have a bigger picture than the individual solution to it. In fact, this function, because it's y squared, it represents two different functions. One is y equal to positive, one is y equal to the negative square root of 1 minus x. So the upper half is the positive one, the lower half is the negative one, and this one represents the whole thing, positive one and negative one. And what we're going to do here, we want to find the tangent line of this graph at 1/2 and root 3 over 2. So we want to find the equation of the tangent line for this. And then there's this issue that you want to find the tangent line, you got to know the derivative, and what is the derivative exactly? That part we're going to calculate it. So in this question, the implicit differentiation is not the only way, because remember you're able to solve for the y. And in this question, the y is positive, so that's y positive. So we know we can use the upper half of the equation. You can solve the y value for the positive y, that is y equal to root of 1 minus x squared. All right, once you have the y formula, you can then find the derivative. That would be 1 over roots of 1 minus x squared. And then you multiply the derivative of the root, which is negative 2x. Right, and then you plug in the 1/2 with the x to find the slope. And then once you got a slope, you already have the point, you can find the equation of the tangent. So this question is possible to do it without implicit differentiation. So why do we still do it with implicit differentiation? Because the implicit differentiation for this question, it actually is a little bit better. As you can see, there are some complicated part when you're trying to find the derivative. Number one, you have to know how to solve for the y. Some of us a little bit, sometimes we have to decide a common y. Is it a positive y or is it a negative? So solving for the y is part of the process. After you solve for the y, you have to find the derivative. So being able to find the root is that thing, and also the interchange. So there's a small steps that might be a little bit harder to find the derivative. All right, so if we do implicit differentiation, what do we do? With implicit differentiation to find the derivative, we will start with the original equation, and we don't have to solve it. We'll just go ahead and find the derivative of the left side and derivative of the right side. If you differentiate the left side and the right side, differentiate both sides, then we see this. Derivative of x squared is 2x. Derivative of the y squared is 2y times y prime. Derivative of the 1 equal to 0. Okay. So you can see the function is pretty, I have to say, it's straightforward to do. The equation itself is not overly complicated. So in the process, there's only y prime, one y prime. So if you want to find the y prime, you move the x term, the 2x plus the y prime. So we have 2y y prime equal to negative 2x. And therefore the y prime would equal to, we divide the 2y, you have negative 2x over 2y. And cancel the 2, you have this negative x over y. That's the derivative. And we need to know the derivative. This is our x and y. The x is negative, the x is 1/2. And the y is 3 over half. So we cancel the 2, it's negative 1 over 3. That's our derivative. That's the slope. Any question? So we'll have our slope of the tangent line. All right, you can see some part of it, this is a formula for the derivative, and then we start plugging the number because we want to know the slope. Now, they're actually similar. Now, what we have here is also have the negative 2x. You cancel the 2, and that equal to negative x over root of 1 minus x squared. You see, if we directly solve the y and find the derivative, we get this. If we solve from implicit differentiation, we have this negative x over y, and this is negative x over this, and that's the original, that's the y, right? This. So even though they look different, they're actually the same, except you're going to have to plug in negative 1/2 of the x, and this is the x there. 1 minus 1/2 squared is 3/4. Root of 3/4 is that number, which is that same number. So with both methods, we're able to find the same slope. This is the slope. Once we get our slope, we can write our tangent line. Equation of the tangent line is y is equal to negative 1 over root 3. And then x minus 1/2, x minus the x value, and then plus the y value. I think we have to copy the wrong number again. This is root of 3. That was the slope, root of negative 1 over 3, and then x minus 1/2. We can confirm that with this. The point is on the first quadrant is 1/2, and the y value is square root of 3 over 2. That's the point. We're drawing the tangent line there, so it's y equals to negative 1 over square root of 3 times x minus 1/2. And yeah, that's what those are. Plus the square root of 3 over. That's you can see the equation that we determined is alpha. Okay, that's the same thing that we find out. Okay, so this is the equation that we determined. Right, this is another example, kind of confirm that you can find it both ways. You can find the direct formula for y and find the derivative. It will be the same as you would find with implicit differentiation. There may be a little bit of deviation from it because when you're trying to find implicit differentiation derivative from formula, you're allowed to use x value and y value to build your formula. But when you're trying to find the derivative using formula y, you only have an x variable on one side because it was calculating the y value explicitly. We're not supposed to have any y here. So your formula is was only x as a variable. You know that they're actually the same because see the root of 1 minus x squared, it is the y value. It's the same as y. But they do provide the same answer no matter which method you use. Any question? This is our first class on implicit differentiation. So let's try it. Let's do some practice tomorrow. That'll be it today. We're okay. Confused? Are you okay so far? All right. Let's work more. Thank you. Yeah, I'll post it one day. Thank you.
Feels like it makes it easier.
Yeah, they should be pointing that works nice.
To be able to-
Because it's giving a circle.
Yeah.
Maybe it just helps me understand it better.
But there's our other point. I mean, it should work for any other one. This one is.
Yeah.
Weird. Huh? Yes, we did a quicker question at the beginning. This is the one that we did. 14.